Okay, hello and welcome. This is a video on the rate laws derived by calculus. So this is a fusion of chemistry and calculus, and it's really just the natural laws of science, which is why Newton and Leibniz invented calculus in the 1600s just to make their stuff work. So it was pretty cool how they did this. And all of calculus is based on things naturally happening, rate of change, and then we're going to talk about areas under curves. But just for chemistry and calculus, this is what we need to know. We're going to take this zero order rate law. Okay, what is a zero order? Well, anything with a power of zero, which, what does this Ka mean? Let me go down here for a moment and look at the other rate law orders first. So zero order is a to the 0, first order is a to the 1, and second order is a to the 2. And if we had a third order, it'd be third would be r equals Ka to the third. Well, right now, we're not going to get that far in most chemistry classes. We just talk about zero, first, and second order rate laws because there's a lot of things happening with the reaction kinetics and the probability of molecules hitting each other. Today, we're just going to say, hey, there's a different power to this thing called concentration. And A could be the concentration of any reactant. So let me go away from the calculus more and talk more about the chemistry of this. Okay, what is R? It's a rate. It's how fast something happens. So in some chemistry books, they'll say rate is going to be a slope. It's going to be the change in concentration of A over the concentration or the change in time. So I don't have the videos here, but maybe I'll insert them. It's a picture of a graph of concentration versus time. So that's called the differential rate law. So in calculus, we don't talk about this delta A over delta T. We're going to talk about a very, very small change in A and a very, very small change in T. And it's so small, we call it a differential, an infinitesimal. And we talk about limits and things going to zero, approaching zero. So just for the mathematics of today, we're going to call it dA dt, which is the change in concentration, which is molarity over time, and typically in seconds. And it could be a lot of things: mole per liter per second, mole, L to the -1, S to the -1. There's all kinds of units that we talk about with rate constants and half-lives and all that jazz. Today we're just going to say it's a molarity over second, just to do the mathematics here. Okay, so R equals K, and anything to the 0 power is 1, and anything times 1 is itself. So I'm going to simplify this to R equals K. And what is R? It's a change in concentration versus time. And just to keep my signs right, if I insert a graph of this A versus T, it's going to look like this. It's going to look like a straight line, which is why I'm probably going to insert a picture of it. And it's a negative slope. So I'm going to say R equals negative K. So therefore, R equals negative dA dt. And that R is equal to negative K. So I'm going to say, I could say negative dA dt equals K, or I can say dA dt equals negative K. And now I'm going to take this equation, which is a derivative, dA dt, and I'm going to move it to both sides. So dA cross multiply equals negative K dt. And then I'm going to pause here and just imagine you know calculus. If you integrate both of these functions on the left-hand side and the right-hand side from initial A to final A, I'll call it A0 and A. I know it's the same variable. And then from T0, which is 0, I'll just put a 0 here, to T2, which I'll call T, and you integrate dA, you just get the variable A and then evaluate it from here to here. So it's going to be a evaluated at a and a0, and then the integral of dt is just going to be t times the negative k. So it's going to be negative k evaluated, excuse me, it's going to be negative kt evaluated from t to 0. In other words, I'm going to take this minus this, a minus a0 equals negative kt minus 0. So just negative kt. And if I add a0 to both sides, a equals negative kt plus a0. And ta-da, we come up with this thing that concentration at any time as a function of time equals negative kt plus a0. It's a linear relationship. And I'll put the brackets around here just to say it's molarity. So let me scroll down here, and this is a very common graph table people see in their books or on the internet. The integrated rate law for a zero order is a equals negative kt plus a0. The graph is linear. A versus t is linear, and the slope is downward. It's negative k. So we'll talk about the first and second, which has a little bit more math involved. This is called an ordinary differential equation. So if you take a differential and integrate it, it's called the integrated rate law. Yay! So that's why it's called integrated, because you integrated an ordinary differential equation. Okay, let's do it for r equals ka to the 1. How is that going to change? Well, you have to know a little bit more calculus, because a simple integral of dx is x minus 0, which is, in this case, a minus a0, which is how I got this one. So let me do the same thing. R equals dA dt, and it's a negative slope. So I'll say dA dt equals negative Ka. This time, the a's have to go together. So I want the a on the side with the dA, and I want the other side to cross multiply. So I'll put this over 1 to make this visible. 1 times dA is dA equals dt times negative Ka. So negative K dt times A. I'm going to divide by A to get it over here. When I divide by A, isn't that 1 over A? So 1 over A dA equals negative K dt. Well, if you know some calculus, you'll say, hey, this looks mysteriously like the one I just did up here. So I'm going to do that. I'm going to say it's negative K. I'm going to integrate both sides from 0 to t, and I'm just going to call it, the integral of dt is t times k, so it's negative kt. And on the left-hand side, it's a little bit more involved. If you know about integrals, a derivative, you subtract 1 from the power. So for an integral, you're going to add 1 to the power. Well, the power is negative 1. So I'm going to get so I'm going to get something to the 0 power. So if you know a little bit of calculus, you know that the derivative of natural log is 1 over. Therefore, the integral of 1 over is natural log. So I'm going to say, going from a0 to a, integrate 1 over a equals ln evaluated from a to a0. So let me put ln of a minus ln of a0 equals negative kt. And that, my friends, using calculus is why a first order, which had a 1 over here, when you move it to the other side, becomes a 1 over a dA. And when you integrate the x to the negative 1, you get natural log of x. Or if you integrate 1 over a, you get ln of a minus ln of a0 from subtracting a to a0. And there's a whole lot of calculus there, and a lot of you people will be in AP Calc. You'll totally understand this. And my neighbor, the teacher I teach with, he's a great AP prep guy, and he helped my daughter 2 years ago, did a really good score in the AP Calc. So I'm a chemistry teacher, and I taught math before, but he really knows his stuff. And he said, oh yeah, this is a good chunk of the AP exam, is knowing these simple integrations of ordinary differential equations called I think related rates, he called them. So when I was helping my daughter in calculus, I'm like, yeah, I kind of remember this, but he was an expert. Thank goodness for him, Mr. Hutzel. Kudos. to you. Okay, so I'm going to say that the integrated rate law, the natural log of A equals, let's add ln of A0 to both sides, equals negative kt plus ln of A0. Ta-da! So right now, let's go down and look at the integrated rate law, and the slope again is negative k. Now, we'll talk about the second order in a moment. So do you see that this rate law and this rate law, it's A, ln A, negative kt, and then A0 plus ln of A0. Looks almost the same. Kind of looks like y equals mx plus b. And that's exactly what it is. That's the y. There's the slope. The slope is the constant, k. And the b is the x-axis where it crosses the initial concentration at time 0. Awesome. Okay, now I'm going to do it for, after I erase my little cube, my third order right here. Now let's go to the second order rate law. And here we go. So R equals dA dt. R equals the change in concentration over time, and that equals a negative k a to the second. So now I can take the integral of a polynomial if it's not -1. Now it's going to be -2 over there. So again, let me take this and cross multiply it over here. dA dt equals negative k a squared. Multiply the dt. So I have dA equals negative k dt times a to the second. And I'm going to move the a down here. When I do, it's going to be divide by 1 over a squared. So it's going to be dA over a squared equals negative k dt. Again, when I integrate this side, very easy, it's negative kt. Okay, but now I've got a, this is a to the 2, so I'm going to make it over here. I apologize, I forgot my k. There's my k. So let me move it over here for a moment. It's going to be a to the -2 dA, and I'm going to integrate that polynomial. So if you know the polynomial rules for integrating polynomials, it's going to be negative something to the -1 power. And it's like, well, what would I need to have to cancel that? I need to have a -1, a to the -1, evaluated from A0 to A. Now, what does all that mean? It means I'm going to take this number minus this number, but it's already a negative, isn't it? So I'm going to go ahead and take these two negatives and cancel them. So I'm going to have a positive kt now, aren't I? This was not the most well designed. Let me show my work over here. Okay, so I've got a to the -1 evaluated from A0 to A equals positive kt. So what does a to the -1 mean? It means 1 over a minus 1 over A0 equals positive kt. And I'm going to move this term over here, in which I get 1 over a equals positive kt plus 1 over A0. And there, my friends, is the second order rate law. And because we had a second order here and we flipped it made it a -2 on the left to integrate the ordinary differential equation, flipping it to the negative sign, that's why I get a to the -1, which is 1 over a. And there we have it. And that's why it's a positive kt, because I had two negatives from the -1 power when I integrated. So this is total nerd time right here. It's like, who gets excited about this? Right now I'm making this video at 9 o'clock on a Thursday night. Only a nerd would do this. Plus, it's a challenge. You know, I had my calculus 20-something years ago, back in 1992. And I'm going to give a shout out, if anybody knows Texas Tech. I was a freshman in 92, and my calc prof was Lawrence Skovanec, who is now the president of Texas Tech. So I got to see him on a press conference like, hey, that was my calc prof. So kudos to Dr. Skovanec. He gave me the knowledge back in fall of 1992 in the Honors Calc 1 class, and when I make this video, I may send this to him. So that, my friends, is what we do with calculus to derive the zero, first, and second order rate laws. Maybe not as neat as a lot of people, but I think it's organic. So I kind of like that. So if you do want to derive, just be safe. Please don't drink and derive. If you need to, leave the deriving to us. And if you don't really like deriving, please let me be your designated deriver. Okay, this is Mr. Hood signing off. Thanks.